Hello and welcome back to lectures in linear algebra, supplemental lectures. In this video, I'd like to talk a little bit about basis and coordinates. So we'll remember that a collection of vectors, which we'll call B here, we'll name the collection B, of vectors x1 through xn of a vector space V. This collection is said to form a basis of B if and only if the collection is both linearly independent and spanning. Okay, and taken together, these two properties mean that for any vector v in our vector space, so for any v in v, we can find coefficients and we can write this v uniquely as a linear combination of these vectors. So v can be represented uniquely. And unique is the key here. It means that there's only one way to do this. So as a linear combination, so v would equal c1x1 plus c2x2 all the way up to cnxn, the sum. Okay, and so this is what we're going to use our basis for. The definition of basis is that it's a collection of vectors that satisfy these two properties, and this is a byproduct of that. Okay, and so just as I said before, then the vector v may be written uniquely as this linear combination, and so then the b coordinates of that vector v, the vector v that we had on the last slide, c1, x1, c2, x2, etc. These basis vectors we consider to be ordered. So we consider this collection to be in a fixed order. Now you can change the order at the beginning if you want, but once you set an order, you have to stick with it. Okay? And so these x1 through xn are always going to be written in this order when we write our unique linear combinations. And then we call the b coordinates of this vector v. We call these the coordinates to be the vertical vector of these constants, the constants required to form the linear combination. Okay, and so this identifies our finite dimensional vector space V with the vector space Rn. So we say that V is identified with, it's not equal to, but it's identified with the vector space Rn. Okay, and so these are our coordinates. And this is going to be very useful for us because now we can write all of our vectors in any vector space as vertical vectors, column vectors, and then everything that we've learned about column vectors and operations with them will apply to our coordinate vectors. So S here in this example is going to be the subspace of symmetric matrices in our 2x2. So that means that a generic matrix in S, if it's going to be symmetric, then it has to obey that its transpose equals itself. So the two off-diagonal elements must be equal to each other. Maybe we should call this D. Okay, so these are the two off-diagonal elements. And this says to write it in standard coordinates. So it's not clear what standard coordinates might mean with respect to this subspace. And I'm not going to prove this is a subspace here, but you should prove that it's a subspace on your own. But as far as the standard coordinates of our 2x2 go, then this matrix here, the symmetric matrix in S, may be written as a linear combination of our standard matrix bases. So these are the matrices with ones in a given slot and then zeros everywhere else. So it'll be A times this matrix plus B times this matrix plus B times this matrix. Those have to be the same, so that constant is the same, plus C times, we called it D, times this matrix, okay? And so then the coordinates of this matrix A, the standard coordinates in our 2x2, right, in this space, the standard coordinates here, usually we use E to denote the standard coordinates, are going to be A, B, B, D, vertically like this. And so now the criterion being symmetric is that these two second and third components of the coordinate vector have to be equal to each other. Okay, so these are the coordinates for this space of symmetric matrices. Again, the standard coordinates are written in the standard basis of our 2x2. Okay, and the second example, the last example on this slide, we're going to consider this basis T of P3. Now this is called T because you could think of this as a Taylor basis, a Taylor series basis. And we want to rewrite this vector P in terms of these T coordinates. And so there's many ways to do this. So the way that I'll do it for this example is to just apply the definition of the Taylor series to this function P of x. So P of x is 2x squared plus 3x minus 1. And its Taylor series, by definition, is going to be P of, in this case, this is a Taylor series centered at -2. So P of -2 plus P prime at -2 times x plus 2 plus P double prime at -2 times x plus 2 squared. And this is in the wrong order. We'll have to change the order to get it in coordinates. But this is going to give us our coefficients. So our coefficients are P of -2, P prime of -2, and this should actually be P double prime of -2 over 2. Okay, there's a 2 factorial here in the Taylor series formula. Okay, so we need to compute these things. So here's our P of x. P of -2 is then going to be what? 8 minus 6 minus 1, so that's just 1. And then P prime of x, the derivative of this as a function, is 4x plus 3. So P prime at -2 is going to be -8 plus 3, that's -5. And finally, P double prime of x is just 4, and so that's equal to P double prime at -2 as well. And so, taking all of this into account, we can then write our polynomial in this expanded form as 1 minus 5 times x plus 2 plus 4 times x plus 2, 4 over 2, sorry, x plus 2 squared. And if we just rearrange to get it in the same order as our ordered basis up here, our ordered basis t, this is 2 times x plus 2 squared minus 5 times x plus 2 plus 1. And therefore, our t coordinates for this vector are going to be, or this vector, which is a function, a polynomial in P3, are going to be in order, right? In the order of the ordered basis, 2 minus 5, 1. Okay, and so that's an example of writing a polynomial as a vertical vector in its coordinates. So thank you for listening, and we'll see you next time.